Hi everyone and welcome to today's Physics Daily Booster. This is number 7 in our paper 2 series, and while it's not explicitly listed on the advanced information for the triple sciences, it is still worth going over because they've not listed anything on P6, which doesn't mean there won't be any questions on it. There are going to be questions, so it's worth doing the booster today. Unit 6 in physics is all about radiation. So when we're considering radiation, first of all, this is something that is emitted at random, and if we want to measure the amount of radiation present, we use a device called a Geiger counter. A Geiger counter actually measures what we refer to as the activity. So the activity, quite simply, is the radiation that's emitted per second, and it's measured in these units becquerels, which have the unit of BQ. One of the important measurements, if you like, for radioactivity is going to be this thing we refer to as half-life. So make sure you know the definition for half-life first of all. It's the time it takes for the activity to halve, or we could phrase it as the time it takes for half of the unstable nuclei to decay. So this is a measure of, obviously, how long it's taking that activity to decrease by 50%. What they can ask you to do is to calculate various things to do with half-life. So this could come from a graph, or it could come just by mathematical calculation. So to give us an example then, a sample of radon 222 has an activity of 100 becquerels. Calculate the activity after 11.4 days. Half-life of radon 222 is 3.8 days. So the first thing we need to do from this question is calculate the number of half-lives. So we're told it's going to be 11.4 days and a half-life is 3.8. So what we need to do first of all is 11.4 divided by 3.8. So as soon as you've got that bit, all you need to do is on the calculator 11.4 divided by 3.8, and that tells us that we have 3 half-lives. So because we've got 3 half-lives, we start with an activity of 100. So what we need to do is basically reduce that 100 by half 3 times over. So easiest way to do it, just use your fractions. Half times a half times a half gives you an 8. Therefore, 1/8 of 100 is 12.5 becquerels. If you're really not good with fractions, you could literally put 100 in your calculator and then divide by 2, divide by 2, divide by 2 again. I think the fractions are easier, but it's up to you how you do it. The other way they could phrase this is by giving us a graph of half-life. So here is our half-life graph. They could ask you to plot one. Remember, math skills come up on these papers. 20% of your physics will be maths-based. Now, on here, what we've got, first of all, our maximum activity is 100, because that's where the line actually crosses your y-axis. So we're starting with 100. If, obviously, we're then going to reduce that by 1 half-life, we'd be coming down to our 50. So if you want to know how long 1 half-life is, use your ruler, come along to the curve, follow it down, and we can see that 1 half-life is actually 4 minutes. So from that, we can just carry on. If you were to go to 25, you come along here, and what do you know, it's 8 minutes. So obviously there we can find out how long the half-life is, just reduce the activity by half, come along and then read off the x-axis. Alternatively, they could actually give you a time and ask you obviously what the number of half-lives is that's passed. So again, you just need to work out how long the half-life is first of all, and then divide that time by 1 half-life. If we now take a moment to think about electron structure again. Now, we did this in our earlier chemistry. Hopefully we remember that as far as the electrons go, then they occupy these energy levels around the nucleus. So different atoms will have different energy levels because obviously they've got different numbers of electrons. The key thing about the electrons is that they're going to occupy the lowest possible energy level. And by that we mean the ones closest to the nucleus. So we can see in the little diagram there, the little shell there labelled 1 is our lowest energy level. whereas 5, the outermost one, that is the highest energy level. What we can actually do is use one thing we call the photon model to try to explain what happens when electromagnetic radiation is emitted and absorbed. So what we actually find in our photon model is that we're going to assign a little name called photon to basically packets of energy. Now, the energy of each photon is going to be proportional to the actual frequency of it. So what we find is to actually excite an electron and move it from its normal energy level to a higher energy level, it's got to absorb a photon of the right amount of energy. Once it's actually absorbed that photon, the electron is going to become excited, it moves to the higher energy level, and we can now say that that atom is in an excited state because we've moved an electron from its normal energy level to a higher one. What we actually find then is if we pass light of all frequencies through a gas like hydrogen, then some of the frequencies are going to be absorbed. It doesn't really matter what gas you use, but they will always absorb light of certain frequencies. Different gases will absorb different frequencies. So from that we can generate something we refer to as an absorption spectrum, like we can see here. Now quite simply, we know that obviously we should have a nice little rainbow pattern there, but we can see there are these little black bars. Now those black bars are representing the frequencies of radiation that were absorbed when the atom became excited. So what we can actually do is by looking at these patterns of those little black bands, we can then use that to work out things like what gases are present in distant stars. So it's useful. It's not just a random thing we do in physics just for actual giggles. This actually has good applications in terms of observing the solar system. Now, what we actually find is if a photon has enough energy, we can completely remove an electron from the atom, and therefore the atom becomes ionized. Which types of photons can ionize atoms? We've got UV, X-rays, and gamma rays. So those three have got enough energy to ionize atoms. The others will just excite them. On the flip side, we now need to think about what happens when those electrons move from the higher energy level to a lower one. And hopefully logic is going to prevail and you can work out they're going to emit radiation. If they have to absorb it to move to a higher one, then when they move to a lower energy level, they must emit radiation. And from that, we get what we refer to as an emission spectrum, which is what we can see here. So the emission spectrum just shows the frequencies of radiation that are emitted as those excited electrons drop back to a lower energy level. And you can see here we've got those 5 bands in our hydrogen emission spectrum. In terms of the frequency of the radiation we're going to emit, that is going to depend on the difference in energy of those 2 levels that the electron moves between. It's also worth remembering here that that change can actually take place either in one big jump, or it could occur as 2 smaller steps or more. If it occurs over 2 or more of those steps, obviously the emitted photons are going to have less energy, lower frequencies, and therefore longer wavelengths. Do remember, and I hope this is a logical point here, that the largest energy difference that we will see will be when an energy level just below ionization is then going to drop back to a lower one. And exactly how much energy that equates to depends on the atom. So if we have a look at 2 examples here, hydrogen and carbon, then hydrogen can emit up to UV photons, but carbon can go further and emit X-ray photons. That's because carbon is larger, therefore it has a greater energy difference between, obviously, the maximum point and the actual lower energy level. Whereas hydrogen, much smaller, therefore only a smaller difference. Do remember as well that protons and neutrons that we find within the nucleus also occupy energy levels. So what we actually find there is that if our protons and neutrons are moving between energy levels, they can actually emit gamma rays because the energy involved in that is going to be so much higher. As always, if there are any bits that you'd like to go over in a bit more detail, then you can use the P6 playlist over on the channel, your revision guides, and as always, I do recommend having a little look at some of those OCR past papers, just get a feel for the kind of questions that come up here. Don't forget to join us once more tomorrow for our next Physics Daily Booster.